The speed of light. Now, Galilean relativity does not apply to electricity and magnetism and optics. And we had an early theory in the late 1800s. Basically, we know from our study of wave mechanics that mechanical waves require a medium to propagate. So the idea is based on this. Therefore, light travels through a medium called ether. Now, what is ether? Well, we can give it some holy meaning. It's the pure air only breathed in by gods in mythology. All right. So, and the speed of light is c only in a special absolute frame at rest with respect to ether. So, therefore, the speed of light is c only in the ether reference frame. And if we have another reference frame, with respect to which ether is moving, or we're moving with respect to the ether reference frame, we have to do a Galilean transformation. Okay, so based on this theory, let's say that this is our ether reference frame, S prime, and in this reference frame, light is traveling to the left at the speed of light c, so that's the speed we measure in the prime reference frame. Now, the question is, what is the speed of light in the lab reference frame, which is the S reference frame that is at rest? So if you remember Galilean transformation, if the S prime reference frame is moving with velocity v to the right, then the velocity of an event measured in the velocity of an object measured in the S prime reference frame is the one measured in S reference frame minus v. So therefore the velocity measured in the S reference frame is ux prime plus v. So we measure a velocity, a primed velocity in this reference frame. We have to add the velocity of S prime with respect to S in order to find the velocity with respect to S reference frame. So in this scenario where the ether reference frame is moving with a relative velocity v with respect to the S reference frame to the left, and the speed of light is c, and light is propagating to the left, because ether reference frame measures the speed of light c, and we measure the velocity of the ether reference frame with respect to our lab reference frame v, these should add up. So we find that speed of light in the so-called downwind direction, as measured by the lab reference frame, should be u prime plus v, which will be c plus v. So this is the downwind direction, that the ether is moving in the direction of the propagation of light with respect to the reference frame at rest. And if the theory is correct, the speed of light is c as measured in the ether reference frame. In the lab reference frame, it should be c plus v. If we change this scenario, if ether is moving to the right, now ether reference frame measures the speed of light c, the velocity direction is to the left. In that case, we have to subtract this velocity for the report on the lab reference frame, so it will be c minus v. That will be the speed of light measured in the upwind direction, so it will be c minus v. Now let's consider another scenario. The S prime reference frame, the ether reference frame, is moving to the left with velocity v. Remember, in that case, we have to subtract the velocity if we are measuring the speed of light with an positive x component here. So let's say that in the S prime ether reference frame, the velocity of the light is c, which makes an angle with respect to the x-axis. Now, in this case, we are basically not in the downwind scenario, we are in the upwind scenario. Why? Because the the motion on the x-axis is to the right, but the ether reference frame moves to the left. So in order to report the x component of the velocity of light in the s reference frame, we have to subtract the velocity of s prime with respect to the s reference frame. So concentrating only on the x component, I see that the x component as measured by s prime reference frame is to the right. It's the propagation of c with respect to the x-axis. Now, because it has a velocity v to the left, I have to subtract that to find the velocity measured by the lab reference frame. As for the y components, since s prime and s reference frames only have a relative motion on the x-axis, not on the y-axis, they will measure the same component of the velocity of light. So therefore, we see that in order to report the velocity of light measured by the S reference frame, the lab reference frame, I have to subtract from its x component the relative velocity of S prime, v, which is to the left, and this is what I see. It's going to be making this triangle, and you can see that I have c square equals u square plus v square. So in order to report the velocity of the light in the lab reference frame, I have to consider this right triangle. Now you can see that the magnitude of the velocity, the speed of light measured in the S reference frame should then be square root of c square minus v square, and it's going to be perpendicular to the ether wind. So the ether is moving on the x-axis, the propagation velocity will be perpendicular to the ether wind with a magnitude square root of c square minus v square. Now, why did I do this exercise? You will see that there is a nice experiment that is going to test this theory. So, as I will mention, all attempts to detect changes in the speed of light basically failed. So, Maxwell's assumption that the speed of light is the same in all inertial reference frames is correct, and it contradicts Galilean relativity. So, using Galilean relativity and the idea that light is propagating in a medium called ether, in which only we have the speed of light c, is not correct, and arguments based on Galilean relativity predict that the speed of light that we measure should change depending on our relative velocity with respect to ether, but all such experiments failed. Therefore, we need to abandon the notions of absolute time and absolute length. So remember, Galilean relativity was based on the idea of absolute time when we did this transformation. All right. So there's this nice experiment, the Michelson-Morley experiment. This is something, Michelson's interferometer was something we mentioned before. It was used to measure the wavelength of light. So the aim of this experiment is determine the velocity of the Earth relative to ether. So we can basically see that the light propagation speed of light should change depending on the direction, relative direction of the Earth and the ether wind. Okay, so let's say that we have aligned this Michelson interferometer so that our ether wind is to the left. So here is our beam splitter. So that splits the beam into two. So the light is incident on this beam splitter. Half intensity is reflected from mirror 1, half intensity is retro-reflected from mirror 2, and in the telescope we can see the fringes due to the path differences of the light that is reflected from the two mirrors reaching to form an interference at the beam splitter. Okay. So arm 2 is aligned along the direction of Earth's motion through space, and now light approaching M2 will have velocity, so this is to the right, c minus v. Why? Because the ether wind is to the left, the light is propagating to the right. In the ether reference frame, the speed of light is c, but the ether wind is to the left, so it's going to be c minus v in the lab reference frame. And when it is reflected, it's now in the downwind direction. The ether reference frame measures propagation speed c, and the light is propagating to the left in the same direction as the ether wind, so it's upwind direction, so it should be c plus v. Now if we rotate this interferometer by 90 degrees, this should change the ether speed between the arms and must shift the observed fringe pattern slightly. The conclusion is that there is no shift observed, and light is an electromagnetic wave that requires no medium for its propagation. So that was the conclusion. Now let's look at the details. So the arm lengths are L, and we model a pulse of light as a particle. Okay, so let's concentrate on arm 2. So how long does it take for the light to approach mirror M2? Because to the right it has the light is moving in the upwind direction. It has the speed c minus v in the lab reference frame. L over c minus v is the approach time. And for the reflected light, which is in the upwind direction, the time is L over c plus v. So that's the distance traveled, that is the speed. So the total time of travel for this pulse of light to approach mirror 2 and reflect and come back to the beam splitter is L over c plus v plus L over c minus v. So that will be Lc minus Lv plus Lc plus Lv divided by c square minus v square. So Lv's cancel, so we obtain 2Lc over c square minus v square. 2Lc over c square minus v square, we divide top and bottom with c square. So we obtain 2L over c parentheses, 1 over c square over c square is 1 minus v square over c square to the power minus 1. So that's the total time the pulse of light spends in the process of reaching M2 and coming back to the beam splitter M0. Now, how about the pulse of light that goes to mirror M1? So this is basically what we have considered here. In this case, we are in the lab reference frame, seeing that the light pulse is propagating in the plus y direction, so it will have this component u. And therefore, and since the ether wind is to the left, that means in the ether reference frame, we should be measuring this velocity of light, c, making an angle with respect to the x-axis. All right, making a finite angle. So therefore, this is what we see in the lab reference frame. Light travels up and down, and therefore this is the direction of u. This is the ether wind direction. This is telling us that the ether reference frame should measure u prime equals c with a finite angle with respect to the x-axis. And therefore we have the speed of light measured in the lab reference frame, square root c square minus v square. We go up L, down L, and we measure the same speed, so it's 2L over square root c square minus v square, because it won't change, the x component is not changing, therefore it won't change whether we're going up and down. So it's going to be 2L over c 1 minus v square over c square to the power minus 1/2. So I multiplied top and bottom with 1 over c. So if you multiply this with 1 over c, it enters as 1 over c square minus v square over c square, square root, which is 1 minus v square over c square to the power minus 1/2. Okay, so the light pulse spans a different time. So in arm 2 it spans this time, in arm 1 spans this time. Now the ether wind velocity is basically due to the fact that Earth has a motion through space, and therefore because the Earth moves with a speed much less than the speed of light, v square over c square is much less than 1. So if we have 1 minus x to the power n, where x is much less than 1, this is approximately 1 minus nx. That comes from the Taylor series expansion. You first evaluate at x equals 0, you get 1, and then you take a derivative n times 1 minus x to the power n minus 1 multiplied by n, and we evaluate at x equals 0 multiplied by x, we obtain 1 minus nx. Therefore, 1 minus v square over c square to the power n is approximately 1 minus n times v square over c square. So, what we do in this experiment is we rotate the interferometer so that arm 1 and arm 2 will exchange roles. Alright, so before the rotation, the time difference for arm 2 and arm 1 is 2L over C. Arm 2 we have 1 plus v square over c square approximately, and for arm 1 we have 1 plus 1 over 2. So we subtract that, minus 1 minus v square over 2c square, ones cancel. So we obtain 2L, we can see here v square over c square minus v square over 2c square is v square over 2c square. So we're going to obtain then 2c cubed. So it's 2lv square over 2c cubed. 2's cancel. We obtain lv square over c cubed. So in the ether reference frame, the time difference between these two arms, arm 1 and arm 2, multiplied by the speed of light c, because in the ether reference frame the speed of light is a constant, it is c, that corresponds to a path difference lv square over c square. Alright, now after rotation, arm 1 and arm 2 will exchange roles. Alright, so we will have the delta t becoming, instead of 1 plus v square over c square minus 1 minus v square over 2c square, it's going to become 1 plus 2v square over c square minus 1 minus v square over c square. So this is going to change sign, and we will have minus lv square over c cube instead of plus. So here we had lv square over c cube. Now it's going to become minus lv square over c cube. And the path difference now, c times delta t after, will be minus lv square over c square according to the ether reference frame. So the change in path difference due to the rotation of the interferometer by 90 degrees will be path difference in the first scenario minus the path difference after rotation, which will be 2lv square over c square. Alright, so one shift of the fringe will have the path difference divided by lambda equals phase difference divided by 2 pi. The path difference is 2lv square over c square divided by lambda, that is phi over 2 pi. So if L is 11 meters, V is 3 times 10 to 4 meters per second, that's the Earth's rotation speed around the Sun, and lambda is equal to 500 nanometers, we obtain 0.44 fringes. So that must be something that is detectable. Minimum detectable shift in the fringe is 0.01 fringe. So this should be something we can see from the telescope. So since we have changed the relative orientation with respect to the ether. Alright, but this is not observed. So basically we conclude that Michelson-Morley experiment shows that Maxwell's assumption is correct. The speed of light is the same in all inertial reference frame, not in this special reference frame called ether, the pure air breathed by gods in mythology. This is correct and contradicts Galilean relativity, and therefore what was wrong in Galilean relativity, we have an absolute time concept in Galilean relativity, so this has to be abandoned. All right. So to summarize, we talked about the speed of light, and Galilean relativity does not apply to electricity and magnetism, and basically we see that from the Michelson-Morley experiment, and Maxwell basically predicts that the speed of light will be the same in all inertial reference frames. The early theory was based on the observation of mechanical waves. Mechanical waves require a medium to move in. However, light does not. And the early theory suggested that there should be a medium called ether, the pure air only breathed in by gods in mythology, with respect to which the speed of light is c, and then we have to consider Galilean relativistic arguments to find the speed of light in our reference frame. So, using Galilean velocity transformation, if the speed of light, if the light propagates in the downwind direction, where ether is moving with velocity v with respect to the reference frame, we should measure c plus v. If it is in the upwind direction, we should measure c minus v. If the light propagates at an angle with respect to the x-axis of the ether reference frame, then we should measure a change in the x component, so it will be in the upwind direction, because light propagation is opposing the direction of s prime in this case. So we should measure cx minus v, but cy should be the same. So this tells us that we form this triangle. This is the speed of light measured in the ether reference frame. This is the motion of ether with respect to Earth reference frame or lab reference frame, and this is what we should measure in the S reference frame, lab frame, which is square root c square minus v square perpendicular to the ether wind. And all such attempts to detect changes in the speed of light failed. Therefore, the reference frame dependence of the speed of light is not correct. It's the same in all inertial reference frames. And this means we need to change our Galilean relativistic arguments. The notions of absolute time and absolute length should change. And this was demonstrated using Michelson-Morley experiment, which is based on the Michelson interferometer, which was rotated by 90 degrees, depending on the relative motion of the Earth with respect to the ether. We should observe a change in the fringes a shift in the fringes that we observe in the beam splitter in Michelson interferometer. If we are in the downwind direction, if the light propagates in the direction of the ether wind, we should measure c plus v. If it's opposing, we should measure c minus v. If we are in the lab reference frame observing that light is moving on the vertical axis, this implies that in the ether reference frame, if it has a speed c, it should be square root of c square minus v squared, the speed of light. So we calculate the total time of approach and total time of reflection, so total time of travel for the light pulse, going to mirror M1, reflecting and coming back to M0, and going to mirror M2, reflecting and coming back to M0 beam splitter. So we do this calculation for arm 1 and arm 2, and the time, according to Galilean relativity, is absolute. So in the ether reference frame, it should take the same amount of time. So we can calculate the total time of travel, the difference between the total time of travel of the two pulses to be Lv square over c cube, because the speed of light c is the same in the ether reference frame for this one or this one. Then we just multiply it by c to get the path difference, lv square over c square. After the rotation, we just exchange the roles of arm 1 and arm 2, so that changes the sign of the delta t, and the path difference is now minus lv square over c square. The total change in the path difference is 2lv square over c square. So rotation of the interferometer should cause a shift in the fringe by an amount 0.44 for typical numbers here. Assuming that the Earth is moving around the Sun, so Earth is moving with respect to the ether reference frame with this speed. So the minimum detectable shift is 0.01 fringe, which is not observed, so this has to be clearly observed, and therefore this notion of the medium ether in which light has to travel is abandoned, and light will have the same speed c in all inertial reference frames, and Galilean relativity is not quite right. We have to abandon the notions of absolute time and absolute length. So in my Galilean transformation, t prime is equal to t should be abandoned, and if I measure the length of an object in s prime or s, those two lengths should be the same in these two reference frames in the Galilean relativity, but that also is not true. So we will talk about Einstein's theory of special relativity, which will account for this.